in and out. So we're now on. We're now being recorded, and so if you have a problem with that, you can turn your screen off. But if you're okay with it, I would much prefer if you had your screen on so that I can see you. Okay, so I have C and I have L, and those are real numbers. So real numbers, one of the things about real numbers is that they fit on the coordinate plane. They fit on a number line. Did you guys ever learn imaginary numbers? Did you learn I? You learned that? Okay, yeah. So you can forget about I. Okay. I mean, if you want to be an electrical engineer, then you got to know I, right? But for calculus, everything is in real numbers. We don't do anything with imaginary numbers anymore. So I, don't worry about I. So these are real numbers. And the function f has a limit L as x approaches c. So let's just talk about it. I'm going to draw a picture that's going to make it more clear. So here is an xy axis. And I'm going to make a function on it. Here is a function. So here's my function f. And I'm going to identify an x value, c. So if I was to look at c on this function here, I can see that I have the point right there on the function. And the y value of that is L. So the coordinates of this point right here are the coordinates lowercase c, uppercase L. Okay. This should come as, so far should come as no surprise to anybody. This is old stuff. Are we okay with this? Okay. Well, what a limit is not that point, but it is a limit is the y value L. So the limit is the y value L as x gets really, R-E-A, let's spell really correctly. That's always a good idea. Gets really, really close to C. So let's kind of visualize what's going on here. Let's just visualize it here. I am on the x-axis and I am moving in this direction. So when I'm right here and I go to my function, you can see that this would be the y value for that x. Is that clear to everybody? You know, if I could get you guys to put on your screen so I can kind of see what we're doing here and make sure that you're following me, it would be helpful. All right. So at this point here, you can see that my y value would be that. Is everybody clear with that? Okay. And if I get a little bit closer here to C, well, I've kind of moved up the function there. And now my y value is over here. And if I get a little bit closer to C, I've kind of moved up the function. And now my y value is here. Right? Now I'm going to kind of go from the other direction. Let's say I was approaching C from this direction. So here's my x value right now. And my y value would be up here. And if I get a little bit closer to C from this direction here, then That's my y value. So what's happening here is that as my x's get closer and closer to c, I am approaching the limit, and we write it like this, I am approaching the limit as x approaches c of my function f of x, and that is equal to L. My y, as I'm getting closer and closer to c, my y value is getting closer and closer to L, to the point where I am going to get so close to c that I am only a point away from c, right? And what's the dimension of a point? Who knows the dimension of a point? How many dimensions does a point have?
2.
Who said that? Natalie, you said that?
Yeah, I said that.
That's exactly right. A point has no dimension, right? So it's kind of a weird concept. But a point has no dimension. I'm that close to C. That brings me that close to L. L is my limit. So let's see if we can't look at a different example here. Okay, so this is how we write it. You need to know this notation. This will be on the final exam. Limits is going to be on the final exam. We're not going to have a separate exam on it, but it's going to be on the final. So I would say the limit as x approaches c on the function f of x equals L. So I'm not, yeah, okay. So I'm not, well, okay, let's just go there. The limit never depends on how the function may or may not be defined at c. Sometimes it's worthwhile to know what the function is at c, and that might help you find the limit, but the limit is not the point CL. The limit is L as x approaches c. So we call this arrow there, we say approaches. So here we have some examples. This blue line right here is this function f of x. It's the function x squared minus 1 divided by x minus 1. I know it looks like a line, right? But this is a rational function. And can everybody see that I have a hole in the line right there? Can everybody see that? Have I shown you that on the calculator, the TI calculator? Have I ever shown you that? No? Oh, well, I'm sorry. We have to pause here because this is like literally my favorite thing on the TI calculator. Okay, so I'm going to call up the calculator and I'm going to go y equals, I got to get rid of my stat plot there. So y equals, I'm going to go parentheses, x squared minus 1 divided by x minus 1. And if I go zoom 6, I'm going to get a line. Okay, so I can see there's a hole in this line at the point 1, 2, but you can't see it on this graph right here with the TI. So I'm going to zoom in. And I'm going to zoom in. I'm going to make my x minimum equal to, I think I'll make it equal to 0. And I'm going to make my x maximum equal to 2. And I'm going to make my y minimum equal to 1 and my y maximum equal to 3. And we'll see if it works. And everybody has to watch the calculator very closely. Everybody watching the calculator? Okay, here we go. I'm going to go graph. Watch it, watch it, watch it. Ah, did you see it? You see the little hole right there in the graph? Yeah, see? So the graph has, that's my favorite thing on the calculator. And I have to tell you, it doesn't work on Desmos. And the reason it doesn't work on Desmos is because really Desmos is better. Because what's the dimensions of a point? We just found out no dimension to a point. So it really shouldn't be there, right? The hole, you shouldn't be able to see that hole. That hole has dimensions. But nevertheless, it's a fun thing to do if you're looking for a hole on your calculator. All right, so I have a hole right here. So I'm going to ask somebody a question. I am going to use the magic bowl here. And let me see, I want to get the right number of people here. So I got 27. So I am asking, Megan, I'm asking you a question. Megan?
Yes.
What is the value of f of 1? So here's 1. What is the value of f of 1?
Zero.
What?
0.
No.
No.
No, not 0. Want to try again, or should I call on somebody else?
Oh, is it nothing? Like,
yes, what do we, there's a technical word that we use for nothing in mathematics. What is it?
no solution?
Well, close, undefined.
Or undefined?
It is undefined, right? Why is it undefined? F of 1, well, here's my function right here. So let's plug 1 in. Well, that would be 1 squared minus 1 over 1 minus 1. So this gets us 0, but it's dividing by 0. You cannot divide by 0. You've seen my t-shirt, right? Dividing by 0. I have a t-shirt about dividing by 0. Have you seen my t-shirt? It's all fun and games, and then somebody divides by 0. Yeah, okay, so you cannot divide by 0, undefined, right? So f of 1 is undefined. All right, so I'm going to ask somebody else a question here. I am asking, Natalia, are you here? Natalia, you were here. I thought I saw you. Did you leave? You walked out on the class, huh? Okay, come back. Let's ask Maddie. Maddie, I saw you too. You're here. You're up in the corner, but you turned off your video. Are you still there?
Yes.
Okay, good. All right. So Maddie, I have a question for you.
Yes.
I am on this function, okay? And my x values are approaching 1. Okay? If my x values are approaching 1, can you see that my y values then are kind of climbing this blue line? Can you see that?
Yeah.
Okay, so I'm approaching 1 from this side here, and then I also want to approach 1 from that side there. So the y values would be going like that. Can you see that?
Yes.
Are you sure?
Yes.
Okay, great. So I want the limit as x, no, I wrote that wrong. Let me erase that here. I want the limit as x approaches 1 of f of x. What is the y value that this function is approaching as I get really, 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 really close to 1?
Is it 2?
Indeed it is. It's 2. That is my limit. F of 1, evaluating this function at 1 is undefined. But I can find the limit as x approaches 1, and that limit is this y value 2. Let's go to this one over here. So, oh, look at this. Oh, now I'm going to ask somebody else a question. You better get this one right. Claudia, are you there with Lauren?
Yeah, she's here.
Okay, Claudia, What kind of a function is this one right here, this g of x right here? What kind of a function is that?
Do you know the answer?
Claudia. You're not muted, Claudia.
I couldn't hear her, but what'd she say?
she was like, I don't know the answer. Do you know the answer?
It must have been funny because everybody's laughing. I wish I'd heard it. All right. What kind of a function is this, Claudia?
I'm not sure.
She says she's not sure.
Oh, I
I
heard
don't know
that.
if I heard
Okay.
her.
So Lauren, do you know what kind of a function this is?
Isn't it like, I don't know what it's called, but it's what we just did like 3 weeks ago.
It's just what we did. What's it called?
Recursive sequence?
No. Good try. But no. We did it before that.
We did it before it. I don't know what it's called, but I know what it is.
I'm going to give one more person a try here. I'm going to give Ivy. What kind of a function is it?
Wait, Claudia got it.
What would she say?
Claudia, say it again.
A piecewise function?
It's a piecewise function. Ivy, you were saved, but I'm going to call you for the next one, all right? This is a piecewise function, right? Because I got 2 pieces to it right here. All right. That's not the real issue here. All right. So, so my piecewise function has this nice blue line. It's got a hole in the function right there, but then it's got this dot right there. Okay, so I got a piecewise function. It's the function x squared minus 1 over x minus 1, the same as we had over here, where x is not equal to 1, but it's 1 where x is equal to 1. That's why we have this. That's why we have this nice going. That's why we have this nice blue dot right there. Okay, so I'm asking somebody else a question. I'm asking Lana. Are you there?
Yeah, I'm here.
Okay, great. This is a function g of x. I want you to tell me what is g of 1. So when I plug 1 into my function g, what is the y value that I get?
Is it undefined?
Nope. Good guess, but
No.
not quite. What is it? Try again.
1?
Yeah, that's exactly right. It is 1, right? Because I go here to x equals 1, and I go up and I see, oh, well, it's the point right there. That's the point that I got. It's 1, 1. Is everybody okay with that? Right? Or if I looked at my piecewise function, it says, well, where x is equal to 1, my y is equal to 1. So g of 1 is equal to 1. Is everybody okay with that? I'm seeing nods. Yes? Okay. All right. Well, I am going to approach 1 on the x-axis over here from the left-hand side. I'm approaching 1. Okay, so we're going to ask this of Bisola. Are you here, Bisola?
Yes.
Okay, great. So my x values are approaching 1. Can you see that where I'm drawing it?
Yeah.
Okay, so that means I'm going up the function here on my y values like that. Are you clear on what I'm doing?
Mm-hmm.
Okay, now I'm going to go from the other side. I'm going to approach 1, which means that along my function, you know, I would have this point here and this point here and this point here, and I would be going like that. Are you with me?
Yeah.
Okay, so what is the limit as x approaches 1 of my function g of x? What y value am I getting really close to?
2.
Louder?
2.
I'm getting, that's 2. You said 2, right?
Yeah.
That's exactly right. I'm getting really close to y equals 2, right? I don't care that this point is right there. That is g of 1. Hey, g of 1, more power to you, right? But the limit as x approaches 1 is the y value that I'm getting really close to as my x value gets close to 1. They are not necessarily the same. Sometimes they'll be the same, sometimes they won't, but I'm looking for getting super close, not quite right there. Let's go to the next one. So my next one is h of x. Oh, and h of x is straight up just a line, right? It's just x plus 1. So that's the line right there. So let's ask Karina, what is h of 1?
2.
H of 1 is 2, right? I mean, I go here to x equals 1. I go right up here. There's my point. My y value is 2. This is the point 1, 2. Or if I really wanted to be algebraic about the whole thing, I could plug it into my formula here, and I'd have 1 plus 1, and that equals 2. So absolutely, h of 1 is equal to 2. Okay. So Sophie, you there?
Yes, I'm here.
Okay, good. All right. So I am approaching 1 from this side right here. And can you see then that as x is approaching 1, my y values are kind of going up along the blue line? Can you see that?
Yeah.
Okay, and my y values are increasing, they're going that way. And if I have x approaching 1 from this side here, can you see that my y values are kind of coming down the blue line that way?
Yeah.
Okay, great. So my limit as x approaches 1 on the function h of x, what y value am I getting really super close to as x approaches 1?
2.
That's exactly right. I'm getting really close to 2. So in this particular case, the limit is actually the same thing as the evaluation of the function at that point. How do we feel about this? We're okay with this? Pretty good? Okay. Okay. So those are with lines, but if you remember the graph of a polynomial function, the graph of a polynomial function is smooth and continuous. So, well, I just want to remind you that polynomial functions are smooth and continuous. Rational functions usually have either a hole in them, or lots of times they have like a vertical asymptote. Okay, so I'm just kind of reminding you what the graphs of those two things look like. In calculus, polynomials are going to be your best friend, right? And we do a lot of calculus with polynomials because they're smooth and continuous. So let's kind of take a look here. All right. So yeah, okay. So we're going to find the limit of a function, and we're going to do it in different ways. We're going to use substitution. We're going to utilize algebra. We're going to utilize graphs, and we're going to utilize tables. So we got a lot of different ways to find the limits of a function. Okay, so this is telling me here that f of x is a polynomial. And c is some kind of real number. Now, magic bowl. Zian, I just said this a second ago, but I'm going to ask you again. The graph of a polynomial is what?
Smooth and continuous.
Graph of a polynomial is smooth and continuous. So when I have a polynomial, that graph is going to look nice and curvy, and it's continuous. It's going to go on forever in either direction. You know, really very nice, easy to work with graph. And what that has to do with limits is that if I take, actually, let's make an x-y axis here so we can kind of see it better. If I take any real number c, so any number on the x-axis, and I take, here's my c, and I go up to my function here, and I find out that this is my, well, this is f of c. This is the value of my function where x equals c. Well, just like we were doing before on that last problem here, as x is approaching c from either direction, my y value is approaching f of c. And because it's a polynomial, I can say that my limit as x approaches c of my function f of x is equal to f of c. So I'm going back to this problem. I'm going back to this problem right here. The only polynomial we had here, let's actually duplicate this page so we can clear out some of this ink. Let's clear the ink. Okay, great. This one here is the only one that's a polynomial. It also happens to be a line, but it's also a polynomial. And we found that as x approaches 1, my y approached 2. And we also found out that h of 1, which was, this right here is like our c, is equal to 2, but also the limit as x approached 1 was also equal to 2, which was equal to h of 1. So when I have a polynomial and I want to find a limit, I have a real easy way of doing it, and that's all. And all I need to do is plug the c into the function that I'm trying to find the limit for, and that's going to give me my limit. We'll do a problem on this in just a second. Actually, maybe let me see if we can do them right now. Yeah, so let's do this problem. Then we'll go backwards to the next section there. So I'm trying to find the limit as x approaches 5 of this polynomial. So let me I want to say this right. Well, let's just leave let's distinguish a rational function from a polynomial. A rational function is really a function fraction. It's f of x divided by g of x. Right? It's a function fraction. This, as you can see, is just f of x. That is a straight up polynomial. So if I want to find the limit as x approaches 5 of this polynomial, piece of cake. All I got to do is take this 5 and substitute it in for x. The limit as x approaches c of f of x is equal to f of c. It's equal to the function evaluated at c. So I'm going to do this. I'm going to take 4 times 5 squared minus 2 times 5 plus 6. So 4 times 5 squared is 25. So this is 100 minus 25 plus 6. No, I did that wrong. 25, 2 times 5 isn't 25. Come on, Glenn, get real here. 2 times 5 is 10. That would be much better, I think. 100 minus 10 is 90 plus 6 equals 96. This is both f of 5, and it is also the limit as x approaches 5 of my function f of x. So am I going too fast, or are we following along? We making sense here? I'm seeing thumbs up. Okay. Let's go back up here and let's look at the second part of this. Let's actually clone this page too. And let's get rid of the ink from this page. So we did section 1 right there. Now let's talk about section 2. So if f of x and g of x are polynomials and c is any real number, well, if I have f of x divided by g of x, I have a rational function, and that is likely to have a vertical asymptote or a hole. It's going to have some problem. But I can still use substitution. I can still substitute c in for x as long as g of c does not equal 0. Because if I plug that in and I find out that this is equal to 0, Megan, if this is equal to 0, what's it going to be?
Undefined.
It's going to be undefined. So I got to make sure that my denominator is not equal to 0. As long as the denominator doesn't equal 0, I can just use substitution to find the limit, no problem. But if the denominator equals 0, I'm going to have a problem. We'll find a method to solve that. So let's see here. All right, here. So let's ask, come on, calculator on. 29. Natalia, did you come back or did you leave forever? No, Natalia, I see you now. You're in the corner. Are you here? Oh, not there.
Mr. Jenkins,
Yes.
can you go back to like the 1, 2 rules so I can take a picture of it?
Right there?
Back a page.
There?
There. Thank you.
Here, you
Mr.
got it?
Jenkins, Natalia's microphone doesn't work, so she's here, but she just can't say anything.
Oh, okay, that's fine. Hi, Natalia. Glad you're here. That's fine. All right. So, all right. So we did that one. So here I have a, well, I'll ask somebody else. 18. So Ari, you here? Ariana, or did you leave me too? Oh. Okay. Claudia, you're back again? Are you still here? You're with Lauren? Oh, we're just striking out, man. Everybody is like taking off. We're gonna have to do something about this. I mean, I know we're getting to the last days of school. I mean, come on, you know? Yeah,
She's
Lauren.
here.
She's here?
Yeah.
Okay. Claudia, is this a polynomial or is this a rational function?
Lauren, okay, polynomial.
It is a polynomial. A rational function is a function fraction, and I don't see any denominator here, so I think this is a polynomial. So if it's a polynomial, so I'll find the limit. Everybody, go ahead and find the limit. It's a polynomial, go ahead and find the limit. So Mia, can you tell me how to set this up?
Would it be f or limit and then x it's -1/2?
Yeah, okay, so how am I gonna find the limit here? Do you know?
I'm not sure.
Okay. Maria, can you tell me how to set it up?
I did half, oh, wait, lim, parentheses, and then half cubed minus half squared plus 1. I don't know if that's right.
Well, you're very close, and I'll show you what you did wrong, which is probably not your fault. So you did 1/2 cubed minus 1/2 squared plus 1. That what you did? Yeah. The only thing you did wrong is, and it's really hard to see, but this is -1/2.
Oh,
Right? So no big deal. I'm sure you got the concept right. You would have put a negative in there, and then a negative in there, right?
yeah.
Okay, so we're substituting. We're taking what we are approaching, and since it's a polynomial, we can just stick it in there for x. So -1/2 cubed would be -1/8 minus -1/2 squared would be +1/4, and then plus 1. So let's get ourselves a common denominator. So I have -1/8 minus 2/8 plus 8/8. So -3. That looks to me like it should be 5/8. And let's see if we are right. 5/8. We win the prize. And let's just take a look at our graph here. So at x equals negative, this is a hard graph to read. It's kind of tiny, right? But if I go negative, you really can't, you just can't see it. And then -1/2 would be like right about here, and it's less than 1. So yeah, it looks like it could be 5/8. So but I'm pretty comfortable with that. So how did we do? We did okay here? Yes? Okay. All right. Well, try this one. Try this one here. Now again, I'm going to point out it says -1/2 here. I want the oh, let me say one more thing. I want to go back up here. Maria and Mia too. When you're finding the limit like this, you don't need to write limit again. Once you make the substitution, then you're finding the number that is the limit. We don't need that limit there again. We'll get used to this notation, but I'm just kind of saying that here. So when you're doing this one here, do your substitution. See if you have a 0 in the denominator. If you don't, then just continue with your substitution. And it's a -1/2. So Nicole, can you tell me how you set this up?
Yes. So I set it up as limit,
Uh-huh.
-1/2 minus 1/2
Uh-huh.
over 1/2 squared.
It's a -1/2 squared.
Negative, yeah.
Uh-huh.
Plus 5 times -1/2
Uh-huh.
plus 25 over 4.
And what did you get as your answer?
I got -1/4.
-1/4. Let's take a look. -1/4. Pretty good. Make sense? Right? So we were able to do that. Now, I just want to say one more thing here on this. Nicole, when you're actually solving for the limit and you're doing your substitution, then you no longer need to write limit.
Okay.
Okay, this is your limit. So this is indicating, hey, I'd like to find the limit as x approaches -1/2 of this function here, but this is your limit, you know, and then you simplified it to be -1/4. So you don't need to write limit again. You found the limit. Am I making some sense? Yeah, it's just a terminology thing. I wouldn't take any points off for it, but it's important to kind of get used to. All right, so if I'm looking at this, I could see that my denominator isn't going to be 0. In fact, I could look at my graph right here, or I could have made a graph on Desmos or my calculator, and I could have seen, well, at -1/2, this is my y-axis right here. And at -1/2 right there, well, I am going to have a value. It's true I have this vertical asymptote right here, but this vertical asymptote is, I don't know, looks like it might be -2.5 or something like that. I don't really need to worry about the vertical asymptote, because at -1/2, as I approach -1/2 from the left and from the right, I can see that my function is actually going to have some kind of a value right there. So I'm okay using substitution. Pretty good? Yes?
For
Okay.
writing the answer like on a test, would we say limit of f of x equals 1/4?
Yeah, well, you would say the limit as x approaches -1/2 of f of x equals -1/4. Or really, if I gave you this problem, your answer would simply be that.
Okay, thank you.
Yeah, just the number. So the thing about a limit is a number. So let's oh, you know what? Let me show you a picture here. Yay, I think it's in the calculus folder. Let's type mom. There we go. So my mom had a birthday a couple years ago, and can you see the cake? Everybody can see the cake? Okay, so actually, let me take a snip here, because they, you know, I mean, I can't really fault the bakery. I don't expect the bakery to know calculus, but let's go here, and let's get a page. Paste it, come on. All right, so what this is really supposed to say here is the limit as x approaches 3 of 10x squared. So what is the limit as x approaches 3 of 10x squared? This is a polynomial. What's the limit of as x approaches 3 of 10x squared?
90?
90.
Yes. So that was on her birthday cake. My mom turned 90. So this, you know, that was her birthday present, right? The limit is a number. So this whole expression right here, I can use that for 90. So if any of you have grandparents that are going to turn 90, this is what you write on their next cake. They turn that. Or if you have, you know, little nieces or nephews, you could say the limit as x approaches 1 of 1 plus x. And then, you know, then they're 2 years old. How exciting is that? See, instead of having just a stupid 2 on their cake, they get this whole fancy thing. I mean, that's like awesome. You're going to breed mathematicians. This is what you want to do, right? So the limit is a number. And that's really why it's so valuable in calculus, is because we can actually assign numbers to these things and manipulate them. Even though we're not right at that point, we're just close to that point where you're going to see how that's really going to be like super helpful. You're going to see that before we're done with pre-calculus, you are going to see the heart of calculus, and it's the differential calculus, and you're all just going to be so aghast that you're going to all turn your screens on so I can see you, and you're going to with, you know, big eyes and an open mouth. I'm telling you. Okay, we will. I'll let you go now. We'll do this problem here when we come back. Wait. Do I need to do something here? No, you already got the test. The test is due on Friday. I already reminded you of that. Go take a longer break, get a cup of coffee, do something fun. All right? Bye.
Yeah.
Jenkins,
Thank
you.
Thank you.
Welcome, guys. See you later.
Thank you.
You're welcome. Goodbye, Claudia.
Bye.
Stop the share.